Every decision you make might be creating another universe. This is the multiverse hypothesis, a real scientific idea that pushes past science fiction. We are going to untangle the solid evidence from the captivating stories, revealing how this concept could shatter our understanding of reality itself. By the end, you will see the cosmos in a completely new way, questioning what is real and what is possible. Could our universe be just one bubble in a frothing cosmic sea? And what would it mean if we found a bruise on the edge of space from a collision with another? How does the simple act of choosing your breakfast spawn entirely new worlds? What does it feel like to consider that every version of your life might actually be happening right now? The sheer scale of this idea can feel overwhelming, so let us break it down. Think of the multiverse not as one single theory, but as a spectrum of possibilities, a family of related ideas. At its heart, the core proposal is almost dizzying. Our entire observable universe, with its hundreds of billions of galaxies, might not be everything. It could be just one island in a vast, perhaps infinite, cosmic archipelago. Each of these other islands could be a universe unto itself, operating under a completely different set of rules. The force of gravity might be stronger, the speed of light slower, or the very number of spatial dimensions could be different. Scientists often categorize these ideas into levels to help us understand their foundations. The most conservative level, often called Level 1, emerges from the theory of eternal inflation. Picture our universe as one bubble in a vast, endlessly expanding cosmic foam. Other bubbles are constantly forming, but the space between them expands so fast that light from one bubble can never reach another. They are real, physical places, but forever isolated from our view. Then there is a more speculative level, Level 3, which springs from the strange world of quantum mechanics. In this view, every time a quantum event has multiple possible outcomes, the universe doesn't just pick one. It branches, realizing every single possibility. Your choice of breakfast this morning did not just spawn one new world, but an infinite number of them, each containing a different version of that moment. Grasping this spectrum is the key to separating scientific inquiry from science fiction. It allows us to see which ideas are grounded in mathematical frameworks and which remain in the realm of pure philosophy. With this map of the multiverse in hand, we can now journey to the specific, powerful theories that predict these other realities actually exist. The idea of an endlessly inflating cosmos offers a startlingly concrete mechanism for creating multiple universes. This process, known as cosmic inflation, was first proposed to solve some of the deepest puzzles about our own universe. Why is the cosmos so uniform in every direction we look, and how did such vast, smooth structures emerge from the Big Bang's primordial chaos? The answer, developed by physicists like Alan Guth and Andre Linde, is that the infant universe underwent a growth spurt of unimaginable speed, expanding faster than the speed of light for a fleeting fraction of a second. This smoothed everything out, much like stretching a wrinkled rubber sheet until it becomes perfectly flat. But the most profound implication lies in what is called eternal inflation. In this view, the driving engine of that hyper-expansion never truly shuts down. It stops in localized patches, and each of those patches becomes a self-contained universe, like a bubble forming in a pot of boiling water. Our entire cosmos is just one such bubble. As physicist Brian Greene puts it, inflation does not end everywhere at once. It ends in patches, and each of those patches becomes a universe. What makes this so compelling is that it is not just a flight of fancy. It is a direct, and for some physicists, an unavoidable prediction of the very models that so accurately describe the universe we see. The mathematics that solve our cosmic mysteries also point to a reality teeming with other worlds. This moves the multiverse from a philosophical concept into a framework with testable consequences. If our universe is just one bubble, then what happens when it bumps into another? While inflation builds other universes far away in the cosmic foam, another theory suggests they are being created right here, right now, with every breath you take. This is the domain of quantum mechanics, where the rules of reality seem to bend and break. For decades, the prevailing view was the Copenhagen interpretation, which says a particle exists in a blurry cloud of all possible states, a superposition, until the moment it is observed. Then, mysteriously, this wave function collapses into a single, definite reality. But what or who does the observing, and what exactly counts as an observation? This inherent fuzziness troubled a young physicist named Hugh Everett. In 1957, he proposed a breathtakingly elegant, and some would say terrifying, alternative. He suggested that the wave function never collapses at all. Instead, every single possible outcome of a quantum event actually happens. When a particle is faced with a choice, the entire universe splits, with each new branch realizing one of those possibilities. There is no mysterious collapse, just an ever-branching tree of reality. As physicist David Deutsch has put it, the multiverse is not a theory, it is a consequence of our best theories. This is the many worlds interpretation. Think of it like this. Imagine you are listening to a song, and you come to a moment where the chord could resolve in two different ways. In the Copenhagen view, you only hear one resolution chosen at random, but in the many worlds view, the universe splits in two. In one branch, you hear the happy major chord. In the other, you hear the melancholic minor chord. Both songs continue to play in parallel forever. This branching doesn't just happen for particles in a lab. It happens for every quantum event everywhere. The radioactive decay of an atom, the path of a photon, even the firing of a neuron in your brain. Every decision you perceive yourself making is simply you becoming aware of which branch you are on. For every choice you made, there is another version of you living out the road not taken. This interpretation is mathematically clean, avoiding the philosophical headache of defining an observer. But the cost is a staggering proliferation of reality. An infinite number of universes are born from every moment, a cosmic explosion of possibility happening in the silent spaces between heartbeats. This quantum foundation offers a completely different path to the multiverse than cosmic inflation, revealing just how deeply the idea is woven into the fabric of modern physics. But if these unseen worlds are real, how could we ever hope to find proof? Yet another path to the multiverse emerges from the most ambitious project in all of physics, the search for a single theory that can describe every force in the cosmos. This is string theory, and its implications for reality are even more radical. It proposes that the fundamental building blocks of nature are not point-like particles but unimaginably small, vibrating loops of energy. The different vibrational patterns of these strings give rise to every particle and force we see, from electrons to gravity itself. To make the mathematics of this theory work, however, requires a shocking feature, the existence of more than the three spatial dimensions we experience. String theory suggests there are up to 6 or 7 extra dimensions, all curled up into shapes so tiny that they are completely hidden from our view. But the true multiverse bombshell came when physicists realized that string theory does not predict one unique kind of universe. Instead, it describes a vast landscape of possibilities. Think of it as a cosmic control panel with an astronomical number of dials. each representing a fundamental constant of physics, like the strength of gravity or the mass of an electron. In this landscape, every possible combination of dial settings represents a stable, self-contained universe with its own unique laws. Physicist Leonard Susskind, who helped pioneer this idea, describes it as a cosmic archipelago with perhaps 10 to the power of 500 different possible universes. That number is so colossal it dwarfs the number of atoms in our observable universe. In this context, our universe is not special or inevitable. It is simply one possible configuration, one that happens to have the right dial settings for atoms, stars, planets, and life to form. This provides a potential answer to one of cosmology's deepest mysteries, the apparent fine-tuning of our universe for life. Why do the constants of nature seem so perfectly calibrated to allow our existence? The string landscape suggests there is no why, there is only a where. We exist in this particular universe because it is one of the rare ones that can support us. This idea of a vast landscape offers a third, powerful scientific argument for a multiverse, one rooted directly in the mathematics of unification. With so many independent lines of theoretical evidence pointing toward multiple universes, from cosmic inflation to quantum branching to the string landscape, the question becomes irresistible. Could we ever find tangible proof that we are not alone in the cosmos, but merely isolated in our local bubble of reality? So the universe seems suspiciously well set up for our existence. Consider the force of gravity. If it were just a fraction stronger, the universe would have collapsed back on itself moments after the Big Bang. If it were slightly weaker, matter would have flown apart so fast that galaxies and stars could never have coalesced. The mass of the electron, the strength of the nuclear forces, even the amount of dark energy, all appear balanced on a razor's edge. Tweak any one of these numbers even a little, and the result is a cosmos devoid of complexity, of planets, of life, of us. This is the fine-tuning problem, a profound puzzle that has troubled scientists and philosophers for decades. It feels as though someone or something dialed in these constants with incredible precision. The multiverse offers a radical way out of this conundrum. If our universe is just one among a vast, perhaps infinite, ensemble of universes, each with its own random set of physical laws, then the mystery evaporates. We should not be surprised to find ourselves living in one of the extremely rare universes where the numbers just happen to come out right. After all, we could not possibly find ourselves in a universe that cannot support observers. This line of reasoning is known as the Anthropic Principle. Philosopher Nick Bostrom likens it to a lottery winner asking why they won. The answer is not that the odds were miraculously in their favor, but that they could only be asking the question if they had already won. The multiverse reframes the question from a why to a where. We are not asking why the universe is fine-tuned for life, but why we observe a universe that is fine-tuned for life. The answer, according to this view, is our cosmic address. We exist in a hospitable neighborhood in a much larger and mostly inhospitable multiverse. This transforms what looks like a miracle into a simple statistical selection effect. For some, this provides a powerful, non-theistic explanation for one of existence's greatest puzzles, bridging a gap between cold, hard evidence and deep philosophical necessity. Yet this solution remains deeply controversial. Does it truly explain anything, or does it merely shift the mystery to a grander, even less testable scale? If the multiverse is the answer, then how do we move from this philosophical elegance to finding a physical crack in the walls of our own reality? The search for these cosmic fingerprints begins with the oldest light in the universe, the cosmic microwave background. This faint afterglow from the Big Bang blankets the entire sky, a snapshot of the cosmos when it was just 380,000 years old. Within this fossilized light, scientists are hunting for anomalies, for scars that might tell a story of a violent encounter with another reality. One of the most tantalizing clues is a mysterious cold spot, a vast region of space significantly colder than its surroundings. Could this be a cosmic bruise, the imprint of a collision with another bubble universe in the eons before inflation pushed it forever beyond our horizon? The idea is that when two such bubbles graze each other, the immense energy of their collision could leave a distinct circular pattern of temperature variation in the cosmic microwave background. While skeptics argue it could simply be a statistical fluke or the shadow of a vast foreground void, the possibility remains electrifying. It transforms the multiverse from a purely theoretical construct into something that might have left a permanent mark on our own sky. This quest for evidence is driven by missions like the Planck satellite, which has mapped the cosmic microwave background with breathtaking precision. Cosmologists are not just looking for one giant bruise, they are analyzing the entire statistical tapestry of the light, searching for subtle patterns in its temperature fluctuations and polarization. Certain twisted patterns in the light's orientation, for instance, could be a signature of gravitational waves from the universe's earliest moments, a time when these other cosmic domains were likely much closer. Finding such a signal would be like discovering a fossil from the multiversal dawn. This painstaking work turns the cosmos itself into a detective story. Every irregularity is a clue, and every strange pattern is a suspect. The goal is to find an anomaly so strange, so statistically unlikely, that the only compelling explanation left is an interaction with something from outside our own universe. This represents a monumental shift, moving the multiverse hypothesis from the philosopher's armchair into the rigorous world of data and observation. It is a direct, if incredibly difficult, pathway to turning a mind-bending idea into a testable scientific proposition. But what if we never find such a bruise? The absence of evidence is not evidence of absence, for the multiverse may hide its secrets in ways we have not yet learned to see. But this entire search for proof runs headlong into a fundamental rule of science. A theory, to be truly scientific, must be falsifiable. It must make predictions that could, in principle, be proven wrong. This is where the multiverse hypothesis faces its most serious challenge from critics. If these other universes are permanently beyond our reach, forever hidden by the impenetrable veil of cosmic inflation, then how can we ever claim the idea is truly scientific? The renowned physicist Paul Steinhardt has been a vocal critic, arguing that an idea that cannot be tested risks becoming a form of pseudoscience. It might feel elegant, it might solve philosophical puzzles, but if it explains everything yet predicts nothing unique about our own world, does it truly belong in the realm of science? A theory that accounts for all possible outcomes risks accounting for none of them in a meaningful way. It is like having a master key that opens every door, which also means it cannot tell you what is behind any specific one. This is the core of the critique. We are asked to believe in an infinite number of universes we can never see, based on theories that are, themselves, still on the frontiers of our understanding. Proponents, however, push back with a nuanced counter-argument. They suggest we may not need to observe other universes directly to find evidence for their existence. Instead, we can look for the fingerprints of the processes that create them. Think of it like this: you cannot see the wind, but you can observe its effects on a field of wheat. You can feel it on your skin. In the same way, if the theory of eternal inflation is correct, it should have left specific, detectable marks on our own universe. The search for a particular pattern of primordial gravitational waves, or a specific kind of anomaly in the cosmic microwave background, is not a search for another universe itself. It is a search for evidence of the cosmic engine that would, as a natural byproduct, manufacture that multiverse. So the debate boils down to a philosophical question about evidence. If we confirm a parent theory like eternal inflation, does that force us to accept all of its logical consequences, even the ones we can never observe directly? Is the success of the recipe enough to prove the existence of all the ingredients, even the ones that vanish from the final dish? This tension lies at the very heart of modern physics, a field increasingly divided between the sheer mathematical beauty of its theories and the hard, empirical requirement for testable evidence. The multiverse stands at this crossroads, a ghost in the machine of cosmology, challenging us to define where science ends and speculation begins. Our cultural landscape is saturated with stories of parallel worlds, a narrative tradition stretching back over 100 years. From the pioneering tales of H.G. Wells to the blockbuster spectacle of the Marvel multiverse saga, science fiction has embraced the concept with open arms. These stories tap into our deepest fascinations with identity and choice. They ask, what if you could meet a version of yourself who made a different life-altering decision, who pursued a different career, or who never experienced a particular loss? This narrative device creates immediate drama and emotional stakes, allowing characters to confront their own potential and their regrets in a tangible, often thrilling way. In these fictional realms, crossing the cosmic divide is often as simple as activating a sleek device or stepping through a shimmering portal. The immense barriers that physics suggests would separate one universe from another are conveniently swept aside for the sake of the plot. Characters seamlessly interact with their alternate selves, exploring worlds where history took a different turn. Yet this narrative convenience glosses over the profound scientific hurdles. The real multiverse hypotheses we have explored suggest these other realms are either forever beyond our cosmic horizon due to inflationary expansion, or are branching quantum realities that we are fundamentally embedded within, not separate from. The causal disconnection is absolute. The energy required to tear a hole in the fabric of space-time to reach another bubble universe is unimaginable, far beyond any technology we could ever conceive. Science fiction, in this sense, acts as a vital cultural playground. It takes a complex scientific idea and runs with it, exploring its philosophical and human implications without being bogged down by mathematical rigor. It has been instrumental in popularizing the multiverse, planting the seed of this staggering possibility in the public consciousness. But this very strength is also its greatest point of departure from science. The fiction presents a multiverse of narrative convenience, where the rules are whatever the story requires. The scientific hypothesis presents a multiverse of physical law, where the rules are rigid, untouchable, and potentially forever beyond our direct experience. Recognizing this distinction is not about dismissing fiction, but about appreciating the different kinds of truth each domain seeks. One explores the human heart, while the other probes the cold, hard structure of reality. One asks what these ideas mean for us, while the other asks if they are even real. This divergence between the multiverse of the imagination and the multiverse of the equations forces a crucial question. If the scientific version is true, what would that profound isolation mean for our place in existence? The equations themselves seem to be telling us we are not alone. When physicists work through the math of eternal inflation or the quantum wave function, the existence of other universes appears not as a speculative add-on, but as a direct, inescapable consequence. It is as if you were solving a puzzle and the only way to make all the pieces fit was to admit there is an entire other box of pieces you have not seen. This mathematical inevitability is a powerful argument, one that suggests the multiverse is not just possible, but necessary for our best theories to be logically consistent. Yet here we confront a deep philosophical rift. Does a mathematically beautiful and consistent theory have to be true in a physical sense? The history of science offers a sobering counterpoint. For centuries, physicists believed in the luminiferous ether, a subtle, invisible medium through which light waves were thought to propagate. The mathematics of wave mechanics demanded a medium, and the ether was an elegant, intuitive solution. It was a beautiful idea, but it was wrong. The Michelson-Morley experiment famously failed to detect it, and Einstein's theory of relativity showed it was entirely unnecessary. The ether was a mathematical crutch that reality had no use for. This is the cautionary tale that critics of the multiverse invoke. They warn against reifying mathematics, against assuming that every elegant output of our equations corresponds to a tangible thing in the world. It is a principle known as ontological parsimony, often called Occam's razor, which advises us not to multiply entities beyond necessity. Postulating an infinite number of unobservable universes, they argue, is the ultimate violation of this principle. It is an extravagant solution that explains everything and yet predicts nothing unique about our own specific world. Proponents, however, insist this case is fundamentally different. The ether was an external concept invented to explain a phenomenon. The multiverse, in contrast, is an internal prediction that falls naturally out of theories that are already spectacularly successful. Quantum mechanics and cosmic inflation are not speculative ideas. They are frameworks that have been validated by countless experiments and observations. We are not inventing the multiverse to fix a problem. We are stumbling upon it as an unavoidable implication of our most robust descriptions of reality. To ignore this implication, they argue, would be to stop our exploration at the most convenient point, not the most truthful one. The tension is profound. Are we being courageous by following the mathematics wherever it leads, even into the dizzying expanse of the multiverse? Or are we being gullible, mistaking the map for the territory and filling the gaps in our knowledge with phantom worlds? This debate forces us to confront the very nature of scientific truth, questioning whether our most powerful tools for understanding the cosmos are guiding us toward a deeper reality or leading us on a magnificent, untestable detour. The quiet hum of the cosmic microwave background might hold a ghostly echo of a long-forgotten crash. Within the eternal froth of the inflating cosmos, our bubble universe is not necessarily alone. The same process that spawns these isolated domains also allows for the possibility of a rare cosmic fender bender. Picture two soap bubbles slowly expanding in a sink, their edges eventually meeting and merging. In the vastness of the cosmic foam, a similar collision between two universes could occur. This would not be a cataclysmic event that shatters stars within our universe. The collision happens on the very edge of our spacetime, a frontier so remote its effects would wash over our entire cosmos as a subtle, coherent pattern. The most likely place to find the scar of such an impact is in the CMB, the oldest light we can see. A bubble collision would imprint itself as a distinct circular asymmetry, a region with a specific temperature gradient that stands out against the primordial background noise. It would be a cosmic bruise, a permanent reminder that our universe once touched another. Scientists have turned this theoretical possibility into a rigorous hunt. Research teams have designed incredibly sophisticated algorithms, digital sieves to sift through the mountains of data sent back by the Planck satellite. These programs are not just looking for any irregularity. They are searching for a very specific geometrical signature predicted by the equations of eternal inflation. The quest has yielded tantalizing maybes. A few candidate features in the Planck data have been identified that bear a resemblance to what a collision might look like. Yet, in every case so far, the evidence has fallen short of being definitive. The signal is incredibly faint, and the challenge is monumental, distinguishing a true multiversal scar from the glare of foreground galaxies, the shadow of cosmic dust, or even just a rare statistical fluke in the data is like trying to hear a single, whispered sentence in a roaring stadium. This painstaking work, however, is what separates a philosophical idea from a scientific one. It represents a direct, active attempt to test the multiverse hypothesis. The search for a bubble collision is a high-stakes gamble. Finding just one confirmed signature would be a revolution in human thought. It would provide the first direct empirical hint that our universe is not the only one, transforming cosmology's most mind-bending possibility from a mathematical consequence into an observational fact. But if the search ultimately comes up empty, the silence will be just as profound, leaving us to wonder if we are truly alone in the cosmic foam after all. A gun is pointed at your head, but its trigger is tied to the spin of a single quantum particle. This is the stark setup of the quantum suicide thought experiment, a device designed to force a choice between two visions of reality. With each pull of the trigger, the particle's spin is measured. In one possible outcome, the gun fires. In the other, it clicks harmlessly. According to the traditional Copenhagen view, this is a gruesome game of chance. You have a 50% probability of dying, and if the gun fires, your story ends. But through the lens of the many worlds interpretation, something profoundly different unfolds. The universe does not choose, it splits. In one branch there is a tragic outcome, but in another perfectly real branch you are still alive, hearing only the click. Now imagine this experiment is set to repeat again and again. From your subjective perspective, what do you experience? You would only ever hear the click. You would only ever find yourself in the continuous sequence of branches where you survive. In the branches where you die, there is no experience, no consciousness to register the event. This leads to a staggering and deeply unsettling conclusion. From your own point of view, in a branching multiverse, you become immortal. You cannot experience your own death because any branch containing that event is one you, by definition, are not in. This is not a proposal for an experiment anyone should ever conduct. It is a philosophical razor sharpened to test the logical limits of the many worlds idea. It forces us to ask what we even mean by the self. Is there a single, continuous you traveling down one branch of the cosmic tree, or are you constantly fracturing into countless copies, each one believing themselves to be the original? The thought experiment highlights a bizarre form of selection bias that operates not on a population, but on consciousness itself. Your continued awareness actively selects for the realities in which you remain aware. While this does not prove the multiverse is real, it showcases the sheer strangeness that erupts when we take the mathematics at its word. It pushes past abstract particles and forces the human experience into the equation, making the implications feel terrifyingly personal. If this view is correct, then death is an illusion for the conscious mind, not because life is eternal, but because the stream of your experience is forever shunted onto a path where life continues. This is where our exploration of the multiverse leads, from the cold equations of cosmology to a confrontation with the very nature of our own existence. Your morning coffee is being sipped by another you in a galaxy impossibly far away. This is not a quantum branching event or a journey through a portal, but the simplest and perhaps most unsettling form of the multiverse. It is called the Level One Multiverse, and it requires no new physics, only a straightforward acceptance of the universe's scale and the implications of infinity. Our entire reality, from the farthest visible galaxy to the phone in your hand, is confined to what we call the observable universe. This is a sphere centered on us, stretching 46 billion light-years in every direction. Its boundary is not a physical wall, but a horizon of information set by the finite speed of light and the universe's age of 13.8 billion years. We cannot see beyond this cosmic horizon, not because there is nothing there, but because light from those distant regions has not had enough time to reach us. Now, here is the crucial step. All our best observations suggest that space itself, on the very largest scales, is flat and likely extends forever. If the cosmos is truly infinite, then the domain we call our observable universe is not the whole show. It is just our local neighborhood, one patch in an endless cosmic tapestry. And in an infinite tapestry woven from a finite set of threads, the patterns must eventually repeat. Every possible arrangement of particles that can exist will exist an infinite number of times. Statistically, there is a distance so vast that you will find a region of space identical to our own observable universe in every detail. Within that region, there is a planet identical to Earth with a person identical to you, living a life identical to yours up to this very moment. This is not a theory about different laws of physics. It is a direct mathematical consequence of an infinite universe governed by the same physics we observe right here. The Level One Multiverse forces a profound shift in perspective. The true strangeness of the cosmos may not lie in the quantum weirdness or hidden dimensions, but in the cold, hard reality of infinity itself. It suggests that every moment of joy, every heartbreak, every single decision is being echoed across the void, not as a possibility, but as an actuality. The strangest thing is not that these copies exist, but that we are forever separated from them by an unbridgeable gulf of expanding space, leaving each of us to experience our own unique story in solitary confinement. But the Level One Multiverse is a place of endless repetition, where every story is told over and over with the same rules. Now, take a step further into the strange, to a place where the rules themselves are rewritten. This is the Level Two Multiverse, a cosmic arena where the fundamental laws of physics are not universal commandments, but local ordinances. Here, the strength of gravity, the mass of an electron, even the number of spatial dimensions we take for granted, are not fixed. They are the outcome of a cosmic lottery that was drawn when each pocket universe was born. The mechanism for this staggering diversity lies in the final moments of inflation. As a patch of space-time cools and transitions from its hyper-expanding state, it settles into what physicists call a vacuum state. Think of this like a vast, complex energy landscape with countless valleys and basins. Where our particular bubble universe landed determined everything about its physical character. It landed in a valley that gave us 4 dimensions, the specific masses for quarks, and the precise strength of the electromagnetic force that makes chemistry possible. But other bubbles landed in different valleys. In one, the vacuum state might have resulted in a universe where the nuclear forces are so weak that atomic nuclei can never form, leaving a cosmos of scattered protons and neutrons, forever dark and sterile. In another, the strength of gravity might be so overwhelming that any lump of matter instantly collapses into a black hole, a universe that blinks into existence and vanishes in the same instant. Some of these domains might have 7 spatial dimensions or forces we cannot even conceive of. Our universe, with its perfect balance for life, is not a special creation. It is a single, habitable oasis in an infinite cosmic desert, most of which is brutally hostile to any form of complexity. This idea draws its strongest support from the vast landscape of possibilities within string theory. The mathematics suggest not one, but a colossal number of stable configurations, each one a potential universe with its own unique physics. This provides a powerful, if speculative, answer to the fine-tuning puzzle. We do not need to ask why the constants of our universe seem miraculously set for life. In a multiverse of infinite variation, it is no miracle at all. We simply live in one of the very few bubbles where the numbers came out right, because we could not possibly find ourselves anywhere else. The question shifts from why our universe is the way it is to a simple statement of location. We are not living in a designed universe, but in a viable neighborhood within a much larger and mostly uninhabitable multiverse. While the Level 1 and 2 multiverses exist far beyond our horizon, the Level 3 multiverse is unfolding right here, inside this very room. It is a reality born from the fundamental strangeness of the quantum world, and it proposes that every possible outcome of every possible event is not just a probability, but an actuality. This is the many worlds interpretation brought to life, a cosmos that never makes a choice, but instead branches at every fork in the road. When you stood before your pantry this morning, the universe did not select cereal or eggs. It divided cleanly and completely into one branch where you are now digesting cereal and another, equally real branch where you are finishing a plate of scrambled eggs. These new universes are not distant realms. They are superimposed upon one another, yet they are causally severed the instant they are born, their paths forever diverging. We are never aware of the split because our own consciousness branches along with the universe. We simply find ourselves on one path, forever unaware of the other versions of ourselves continuing their lives on roads we did not take. Physicist Max Tegmark, who developed this level-based framework, makes a compelling case for this view. He argues that the Level 3 multiverse is actually the most parsimonious explanation we have. It does away with the mysterious, ad hoc process of wave function collapse that other interpretations require. There is no magical moment where observation forces a single reality into being. Instead, the mathematics just runs its course, with a quantum wave function smoothly evolving to encompass all possibilities. Every potential history, every conceivable future is real and is being lived out in full. This single, unbroken wave function is the entirety of existence. This idea strikes at the core of our everyday experience. It challenges our most basic intuition about cause and effect, suggesting that the single, linear timeline we perceive is a profound illusion. The concept of free will is turned on its head. You are not making a choice that alters one future. You are a passenger on a train that is constantly, endlessly splitting at the switches, with a new copy of you boarding every possible destination. Every regret, every moment of relief, every what-if is not just a thought. According to this view, it is a reality playing out in a universe forever hidden from your view. But this cosmic isolation is not the final word. A far more radical proposal suggests that our solitude is an illusion, because our universe itself might be a projection. This is the holographic principle, an idea that emerges from the fiery physics of black holes and the intricate world of string theory. It proposes a reality so counterintuitive it seems pulled from science fiction. All the information that describes everything within a volume of space, every star, every planet, every one of us, could be perfectly encoded on its two-dimensional boundary. Think of a hologram on your credit card. The flat, shiny surface contains all the data needed to project a seemingly three-dimensional image. In a similar, though vastly more complex way, our universe of three spatial dimensions might be a grand holographic projection from a two-dimensional surface at the cosmic horizon. This leads to a staggering new vision of the multiverse. If our universe is a projection from its own unique boundary, then other universes could be projections from their own separate, non-interacting screens. This would be a holographic multiverse, a collection of cosmic films playing simultaneously in the same theater, but on different, isolated canvases. The very laws of physics we take as fundamental, gravity, light, quantum mechanics, would not be the root reality. They would be emergent properties, a consequence of the specific way information is encoded and processed on our distant, two-dimensional surface. The reason our universe has 3 spatial dimensions and not 2 or 5 would simply be a quirk of the code on our particular screen. This is not just a philosophical curiosity. It is a mathematically rich framework that physicists like Leonard Susskind and Gerard T. Hooft have developed to solve profound puzzles, particularly the famous black hole information paradox. The mathematics suggests that the information swallowed by a black hole is not destroyed, but is instead smeared and stored on its event horizon, the point of no return. This single insight, scaled up, gives us the holographic principle. If true, it means the vast three-dimensional cosmos we perceive, with its billions of galaxies and its potential for infinite branching realities, is a magnificent shadow play. Every event, every life, every other universe in the multiverse would be a consequence of data processing on a distant, fundamental surface we can never touch. It redefines existence itself, suggesting that the solidity of the world is a deep and persistent illusion, and that the true nature of reality is written in a language of information on the ultimate boundary of everything. A black hole is not a gateway but a one-way street into oblivion. The fantasy of plunging into a singularity and emerging in another universe is a powerful narrative device, but the physics paints a far more destructive picture. The event horizon is not a shimmering portal. It is a point of no return, a boundary where the gravitational pull becomes so intense that not even light can escape. Once an object crosses this threshold, its fate is sealed. There is no going back, no sending a message, no changing course. The very fabric of space-time within a black hole flows inward, like a river rushing toward a waterfall, carrying everything with it. Some solutions to Einstein's equations of general relativity do hint at a theoretical backdoor. An Einstein-Rosen bridge, more commonly known as a wormhole, mathematically connects one region of spacetime to another. In theory, this could link our universe to a different one, perhaps even erupting as a white hole, spewing matter out into a new cosmic domain. But these are not stable tunnels you could travel through. They are incredibly fragile structures that would snap shut instantaneously, crushing anything inside to a point of infinite density. To prop one open, to make it traversable, would require a form of matter with negative energy density, a substance that pushes space apart rather than pulling it together. We have no evidence such exotic matter exists or can exist in the quantities needed. Even if you could somehow construct a stable wormhole, the journey itself would be unsurvivable. As you approach the central singularity, tidal forces would pull you apart. The difference in gravity between your head and your feet would stretch you into a long, thin stream of atoms, a process physicists grimly call spaghettification. You would be shredded by extreme radiation and crushed into non-existence long before you could reach any hypothetical exit. The information that was once you would be lost to the void, or perhaps encoded on the event horizon as the holographic principle suggests, but your journey would be over. This stark reality forces a difficult conclusion. Black holes are far more likely to be the ultimate endpoints for matter and information than they are to be gateways. They are cosmic dead ends, not interuniversal freeways. This profound isolation reinforces a central theme of the scientific multiverse. If other realities exist, they are likely separated from us by insurmountable barriers, whether they are infinite stretches of inflating space, the silent branching of quantum possibilities, or the absolute boundary of an event horizon. The real multiverse is not a place we can visit. It is a shadow we may only ever infer from the faintest of clues left in our own lonely cosmos. Does your awareness of the world somehow bring it into being? This question lies at the heart of one of the most contentious debates in quantum mechanics. In the traditional Copenhagen interpretation, the blurry cloud of possibilities that defines a particle state only snaps into a single, definite reality at the moment it is measured or observed. But what exactly qualifies as an observer? For some, this opened the door to a startling possibility that consciousness itself is the ultimate catalyst, the mysterious ingredient that collapses the wave function and solidifies reality. The physicist John Wheeler took this idea even further with his concept of a participatory universe, suggesting that we are not just passive spectators but active participants in the cosmos, bringing the universe into existence through the very act of observation. It is a profound and almost mystical proposition, placing the human mind at the center of the cosmic drama. Yet this view creates a deep philosophical puzzle, often called the measurement problem. Where do we draw the line between a conscious observer that can collapse a wave function and a complex but unconscious measuring device that cannot? Does a cat in a box count, or only a human scientist? The many worlds interpretation sweeps this entire problem aside. In this view, there is no special moment of collapse, and consciousness holds no privileged power. The quantum wave function never chooses. It simply evolves, and every possible outcome is realized in a new, branching universe. When you look at a quantum system, your own consciousness does not force a single result. It splits just like everything else. One version of you sees the particle spin up, while another, equally real version sees it spin down. Your stream of awareness is simply carried along one specific branch of an endlessly dividing tree. This makes the theory remarkably clean and objective. The multiverse described by many worlds does not depend on the presence of observers at all. It would exist in all its branching glory, even if every living being vanished. Consciousness is not the author of reality, but a complex phenomenon that emerges from the physical interactions of particles in the brain. It is a passenger on the journey, not the driver. This demystifies our place in the cosmos, grounding our most intimate experience, our own awareness, in the same physical laws that govern everything else. So, the next time you make a choice, remember that you are not creating the other possibilities. You are simply living out the one you are on, while countless other versions of you are living out all the rest in a reality that needs no one to watch it unfold. The solidity of the world around us could be an illusion of processing power. Our universe, with all its galaxies, stars, and conscious life, might not be the base layer of reality but an advanced digital construct, a simulation running on a supercomputer of unimaginable scale in another universe. This is the simulation hypothesis, a modern philosophical idea that reframes the multiverse in technological terms. Philosopher Nick Bostrom formalized this startling proposition by breaking it down into a simple logical trilemma. He argues that at least one of three statements is almost certainly true. First, that virtually all civilizations at our level of development go extinct before they can create realistic simulations. Or second, that advanced civilizations have no interest in running vast numbers of simulations of their own history. If both of these are false, then the third statement must be true, that we are almost certainly living in a simulation. The reasoning is one of pure statistics. If even one advanced civilization exists and decides to run countless simulations of conscious beings, then the number of simulated minds would vastly outnumber the one original biological population. Therefore, if you are a conscious being, the odds are overwhelmingly high that you are one of the simulated ones, not an original. This creates a different kind of multiverse, not of inflating bubbles or branching quantum paths, but of nested digital realities, each running on its own server in a higher-level universe. It shares the core multiverse theme of multiple, coexisting realities, but its engine is code and computation, not cosmology. The laws of physics we work so hard to decipher would be merely the simulated rules of the program, the local bylaws of our particular reality. A glitch in the matrix, like a déjà vu experience or a strange particle behaving unexpectedly, could be written off as a cosmic software bug. Yet for all its cultural resonance, this hypothesis stands on a fundamentally different foundation than the scientific multiverses we have explored. It is built on speculative futurism and probability theory, not on the mathematical frameworks of general relativity or quantum mechanics. The inflationary and quantum multiverses are direct, and to many physicists unavoidable, consequences of our most successful theories. The simulation hypothesis, by contrast, is not predicted by any fundamental law of physics. It is an argument from likelihood, not from physical necessity. It also sidesteps one of existence's ultimate questions. It does not explain why there is a universe at all. It simply pushes the mystery back one level. Who or what created the universe that built the computer we are running on, and what created that one? This infinite regress offers no final answer, only a postponement of the mystery. So while the simulation hypothesis is a captivating thought experiment that forces us to question the nature of our reality, it remains a branch of philosophy. It intersects with the scientific multiverse in its mind-bending implications, but it belongs to a different category of thought, one rooted in information and probability, leaving the equations of fundamental physics untouched. The weight of a single choice could ripple across the cosmos. If every fork in the road creates a new reality, then our lives are not just personal journeys but cosmic generators. This is the staggering ethical weight of the multiverse. The idea of infinite copies might seem to drain our decisions of their power. Why agonize over a career change or a difficult conversation if somewhere another version of you is already living out every alternative? This line of thinking leads toward a kind of existential nihilism, where nothing we do is unique or ultimately significant because it is all happening elsewhere. Yet other philosophers turn this logic completely on its head. They argue that if the many worlds interpretation is correct, then your choices are more profound than you ever imagined. You are not just choosing your own path. With every decision, you are responsible for bringing an entire universe into existence. The version of you that chooses kindness over cruelty is not just a better person. They are actively creating a whole reality where that kindness echoes forever. In this view, we are not insignificant specks, but universe makers with every thought and action. This perspective forces a radical redefinition of responsibility. But this generative power has a dark twin. If every possible reality exists, then there are branches of the cosmic tree where suffering is not just a tragic exception but the fundamental rule. There are universes where beings are trapped in perpetual agony, where civilizations collapse in endless cycles of despair. If we accept that these realities are just as real as our own, does that knowledge impose any moral duty upon us? We are causally severed from these other worlds, forever unable to reach out a helping hand. Are we then simply bystanders to an infinite tragedy? This question has no easy answer, but it compels us to expand our circle of moral concern beyond the horizons of our own spacetime. It challenges our most basic concepts of identity. If countless versions of you are living out every conceivable life, then who or what are you? The feeling of a single, continuous self may be the ultimate illusion, a temporary knot in the ever-branching river of consciousness. The multiverse does not just shatter our picture of the cosmos, it shatters our sense of self. It moves the discussion from the clean lines of physics into the messy, profound realms of ethics and philosophy, forcing us to find meaning not in our uniqueness, but in our specific, irreplaceable position within an infinite tapestry. But for every voice championing the multiverse, another rises in stark opposition. The idea of a cosmic archipelago is far from settled science, and its most prominent critics are not on the sidelines but are giants in the field. Nobel laureate Roger Penrose views the multiverse hypothesis as a dangerous detour from the very heart of scientific inquiry. He argues that a theory which cannot be tested, which makes no unique predictions for our own world, is not science at all, but a form of metaphysics. For Penrose, the multiverse is an act of surrender, an admission that we have given up on finding a deeper, more elegant explanation for our universe's properties. He offers his own compelling alternative, conformal cyclic cosmology, a vision of an endlessly repeating cosmos where each eon gives birth to the next in a cycle stretching to eternity, all without needing an infinite number of unseen worlds. This model seeks to solve the same cosmic puzzles, but it strives to keep its answers firmly within the realm of potential observation. Another formidable critic, physicist Lee Smolin, proposed a different kind of cosmic reproduction. His theory of cosmological natural selection suggests that new universes are born inside black holes, with the laws of physics mutating slightly with each generation. Universes that are prolific at producing black holes would have more offspring, leading to a cosmic evolutionary trend favoring universes like our own. This is a form of multiplicity, but it is a constrained and testable one, a far cry from the infinite, unobservable ensemble of the multiverse. The core complaint from these and other scientists is that the multiverse risks becoming a theory of last resort. If a theory can accommodate every possible outcome, then it ultimately explains nothing in particular. It is like having a master key that opens every door, which also means it cannot tell you what lies behind any specific one. This, the critics warn, drains science of its predictive power and its ability to falsify ideas. They advocate for patience and ingenuity, believing that the apparent fine-tuning of our universe is not a sign of a hidden multiverse, but a clue pointing toward a deeper, more unified theory we have yet to discover. This rigorous, healthy skepticism is the engine of scientific progress. It ensures that even the most beautiful and mind-bending ideas are subjected to the fire of debate, forcing us to demand more than just mathematical elegance before we rewrite our concept of reality itself. Our physical reality might be nothing more than a mathematical structure. This is the breathtaking leap proposed by physicist Max Tegmark with his mathematical universe hypothesis. He pushes the idea of the multiverse to its absolute logical extreme. It is not just that our universe is beautifully described by math, which it is, but that every single self-consistent mathematical structure actually exists as a physical reality. In this view, the cosmos is not merely underpinned by mathematics, it is mathematics. Think of every possible equation, every geometric form, every logical system you could write down. If it is free of internal contradictions, it describes a real, physical universe somewhere in the multiverse. Our own cosmos, with its galaxies, quantum fields, and the force of gravity, is simply one specific mathematical structure, the one whose equations happen to match what we measure in our experiments. This is a form of radical Platonism, where the abstract world of numbers and the physical world we touch are not just connected, they are one and the same thing. The number pi is not just a description of a circle, it is as real as the circle itself, existing in a concrete, physical sense. This leads to an answer for one of the most profound questions we can ask: why is there something rather than nothing? The mathematical universe hypothesis suggests that true nothingness, a state of no mathematical structures at all, is logically unstable or perhaps even impossible. A rich, complex, and teeming multiverse is not an accident, but the only logical possibility. Every universe that can exist does exist simply because the math allows it. This is the most comprehensive and extreme version of the multiverse, one that completely dissolves the boundary between physics, mathematics, and philosophy. It suggests that at the absolute core of everything, beneath the illusion of space and time and matter, lies a silent, eternal, and purely mathematical truth. The faintest whisper in the cosmos could tell us if we are surrounded by other worlds. Scientists are now listening for the echoes of creation itself, searching for primordial gravitational waves. These are not the recently detected ripples from colliding black holes, but something far more ancient and profound. They are tremors in the very fabric of space-time, generated in the first furious moments of the universe's inflationary growth spurt. Finding them would be like hearing the distant rumble of the Big Bang's engine. The most promising place to find this whisper is etched into the oldest light we can see, the cosmic microwave background. As these primordial ripples passed through the hot, dense plasma of the infant universe, they would have twisted the light's orientation, leaving a distinct swirling pattern known as B-mode polarization. It is a unique signature, a ghostly fingerprint of inflation's violent birth. This is the holy grail for experiments like the BICEP telescope at the South Pole and the Future Light Bird satellite mission. They are essentially building the most sensitive ear ever conceived, tuned to listen for the universe's first vibrations. A clear, unambiguous detection of this signal would be one of the greatest discoveries in the history of cosmology. It would confirm that cosmic inflation truly happened, providing a stunningly detailed snapshot of the universe in its first trillionth of a second. And this is where the path leads directly to the multiverse. Many of the most robust models of inflation are eternal, meaning the process that created our bubble universe never stops, continually spawning new domains. Confirming the engine of inflation is real would powerfully validate the very mechanism that can, and according to the math, does manufacture a Level 1 or Level 2 multiverse as a natural byproduct. We would have strong evidence for the cosmic foam itself, yet the stakes are equally high if the search comes up empty. As our instruments grow more sensitive without finding the telltale swirls, it places ever tighter constraints on the simplest and most compelling models of inflation. If the primordial gravitational waves are too faint to ever detect or entirely absent, it would force a major rethink. Scientists would have to explore more complex and exotic versions of cosmic inflation, some of which may not lead to an eternal, multiverse-generating process at all. This intense search illustrates a crucial and often misunderstood point. The multiverse hypothesis is not entirely untestable. Its fate is deeply entangled with specific, verifiable predictions about our own universe's deepest history. We may never peer into another world directly, but by confirming the physics that demands their existence, we can infer the reality of the cosmic archipelago from the safety of our own shore. The hunt for these ancient ripples is therefore a critical proxy war in the battle to ground our most expansive cosmic ideas in hard, empirical evidence. A black hole's appetite for information creates one of the most vexing paradoxes in all of physics. On one side stands quantum mechanics, which insists that information, the detailed blueprint of what fell into the black hole, can never be truly erased. It might be scrambled, but it must be preserved. On the other side stands general relativity, which describes a black hole as a one-way street to a point of infinite density, where the very concepts of space and time break down. From this perspective, the information is gone forever, irretrievably lost. This is the information paradox, a fundamental conflict between our two most successful theories of reality. To resolve it, some physicists have been forced to consider a radical escape route, one that leads directly to the multiverse. What if the information is not destroyed inside the black hole, but simply relocated? The provocative suggestion is that deep within a black hole, the intense gravitational field could cause spacetime to pinch off, forming a separate, self-contained region, a baby universe. In this view, every black hole is not a dead end, but a cosmic womb giving birth to an entirely new reality. The information about the star, the gas, or the spaceship that fell in is not lost. It is simply transferred to this new domain, a universe forever causally severed from our own. This generates a multiverse of a completely different character. Instead of an endlessly inflating foam or a constantly branching quantum tree, this is a multiverse born from gravitational collapse, a cascade of new realities spawned by the death of stars. While this remains a highly speculative idea, it powerfully demonstrates how the multiverse is not just a philosophical curiosity. It emerges as a potential solution to the deepest, most intractable problems in theoretical physics, bridging the cosmic scale of general relativity with the subatomic world of quantum mechanics. It suggests that the birth of new worlds might not only happen in the fiery dawn of cosmic inflation, but also in the silent, dark graves of collapsed stars. Your chance of suddenly phasing through a solid wall is so small it is effectively zero in our world. Yet in the infinite sprawl of the multiverse, that minuscule probability is a guarantee. In a cosmos where every possible quantum event is realized, the very idea of improbability begins to unravel. What we call a 1 in a trillion chance is not a rare event, but a commonplace occurrence across the cosmic whole, happening an infinite number of times. This transforms probability from a fundamental law of reality into a deeply personal measure of your own experience. When you flip a coin and see it land on heads, you are not witnessing a 50-50 random outcome. You are simply inhabiting the branch of reality where that particular result occurred, while an identical copy of you inhabits the branch where it landed on tails. The odds were not in your favor, they were merely a label for which path your consciousness would follow. This redefinition touches everything. It challenges how we interpret quantum mechanics, where probabilities are foundational. It questions cosmology, where the initial conditions of our universe are often described as wildly improbable. Even the basic tools of statistics, which we use to predict everything from election results to the weather, are built on the assumption that probability reflects an objective feature of a single reality. In a multiverse, that foundation crumbles. The roll of the dice, the decay of an atom, the path of your life, all of these are not governed by chance, but by the certain, infinite branching of existence. Probability becomes the story we tell ourselves to make sense of the single thread we are able to perceive, a comforting local illusion that vanishes into absolute certainty when you behold the entire tapestry. The relentless tick of the clock might be the greatest illusion of all. The multiverse hypothesis doesn't just add more space to our reality, it completely shatters our conventional understanding of time itself. We experience life as a sequence of moments, a flowing river from the past into the future. But according to Einstein's theory of relativity, this flow is not a fundamental feature of the cosmos. In what physicists call the block universe view, past, present, and future are not successive. They all exist simultaneously, eternally laid out in a single, four-dimensional block of spacetime. Your birth, your life, and your eventual end are all equally real, fixed points in this vast, frozen sculpture. The multiverse takes this dizzying concept and expands it to a scale that is almost impossible to grasp. It generalizes the block into a multi-block, a sprawling landscape of these eternal blocks, each one a complete and finished universe. Within this framework, the branching of the many worlds interpretation is not a process happening in time. It is the construction of the multi-block itself. The universal wave function, as it evolves, is not moving through time but is actively weaving the entire, complex tapestry of all possible histories and futures into a static, eternal structure. This means there is no single, universal now. Instead, there are countless simultaneous nows, each one a present moment being experienced in a different branch. While you are listening to this sentence, another version of you is just being born, and another is taking their final breath. All these moments are equally real and exist concurrently in the multi-block. So what then is the flow of time that we feel so viscerally? It may be a profound psychological artifact, a side effect of how consciousness navigates this frozen landscape. Your awareness is not moving through time, it is simply tracing a single, predetermined thread through one specific block in the multi-block. The feeling of the past being fixed and the future being open is an illusion generated by your limited perspective, like a train passenger seeing the landscape as a blur of motion while the entire route already exists laid out on the tracks. The multiverse, therefore, reconfigures temporality at its most fundamental level. The passage of time is not a river flowing through the cosmos, but a local and emergent property, a story our minds tell us as we journey along one solitary path in an infinite, unchanging forest of realities. We might finally explain why our universe seems so perfectly tuned for life, only to face a question that is even deeper and more profound. Why does this cosmic engine, this mechanism for creating multiple universes, exist in the first place? If eternal inflation is the process that spawns the cosmic foam, why are the laws of physics precisely the kind that allow for eternal inflation? If the quantum wave function branches endlessly, why is reality built on a foundation that permits such endless branching? We can try to push the explanation back one step further, suggesting a meta-multiverse, a collection of different multiverse-generating mechanisms. Or we can appeal to the mathematical universe hypothesis, where every possible set of laws simply exists. But this path leads to an infinite regress, a hall of mirrors with no final reflection. Why that particular meta-structure? Why that specific mathematical truth? At the very end of this chain of reasoning, science may finally hit a wall. We might reach a set of ultimate, brute facts, fundamental rules for which there is no deeper explanation. The multiverse could be the final stop, the outermost boundary of physical explanation. This does not make the idea wrong or unscientific. It simply acknowledges a humbling possibility that our quest for understanding may eventually run up against the inherent, inexplicable structure of existence itself. Some questions may have answers that are forever beyond our reach, not because they are supernatural, but because they form the unchangeable bedrock upon which everything else is built. The multiverse might be that bedrock, the final answer to our chain of why, forcing us to accept that reality, in its ultimate form, simply is. A married bachelor cannot exist even in the infinite multiverse. This is the crucial line that separates scientific speculation from pure fantasy. While blockbuster films present a cosmos where you can hop between realities to meet your evil twin, the scientific versions are far more rigid and, in a profound way, lonely. You cannot visit these other worlds. The energy required to tear a hole in space-time is unimaginable, and the causal separation imposed by eternal inflation or quantum branching is absolute. The multiverse is not a cosmic subway system. It is a collection of islands forever drifting apart in an ever-expanding sea. Another common misunderstanding is that the multiverse means anything you can imagine is happening somewhere. This is not the case. The scientific multiverse is governed by the same ironclad rules of logic and mathematics that underpin our own reality. It contains every possible universe that is physically consistent, not every universe you can conceive of. A square circle cannot exist. 2 plus 2 cannot equal 5. The laws of physics may vary from one bubble to the next, but the laws of reason do not bend. What the multiverse does allow for is every possible outcome of a given set of physical laws. If the constants in another universe permit gravity to be slightly stronger, then stars will burn faster and lives will be shorter, but that universe will still operate on a coherent, logical foundation. This distinction is vital. The public often sees the multiverse as a free-for-all of imagination, a place where magic is real. Scientists see it as a structured, mathematical consequence of our most robust theories, from quantum mechanics to cosmic inflation. It is a prediction, not a playground. Bridging this gap between captivating fiction and disciplined theory is one of the great communication challenges of modern physics. The goal is not to drain the wonder from the idea, but to replace a simplistic fantasy with a far more profound and staggering reality. A cosmos whose true structure is revealed not by ignoring the rules, but by following them to their ultimate, breathtaking conclusion. The quest for a cosmic Bruise is far from over. In the coming decades, a new generation of eyes will scan the heavens, instruments of such breathtaking sensitivity they could detect whispers from the dawn of time. The hunt in the cosmic microwave background will intensify, with satellites and high-altitude telescopes designed to map its subtle temperature variations and polarization with a precision we can scarcely conceive of today. They will sift through the fossilized light not just for one giant cold spot, but for more subtle statistical oddities known as non-Gaussianities. These are patterns that deviate from the standard random fluctuations, potential imprints of the universe's violent pre-inflationary phase, or even the subtle textures left by interactions with other domains in the greater multiverse. Finding them would be like discovering a crack in the eggshell of our own cosmos, a hint of what existed before the Big Bang itself. Alongside this, a new ear is being built to listen to the universe's oldest sounds. Next-generation gravitational wave observatories operating in space will probe a far quieter frequency band. They aim to detect the primordial gravitational waves from inflation itself, the faint rumble of the cosmic engine that started it all. The specific characteristics of this signal, its strength and pattern, would act as a fingerprint, allowing us to distinguish between different models of inflation. Some of these models inevitably lead to an eternal, multiverse spawning process, while others do not. Catching this whisper would tell us which engine built our reality, and whether it naturally manufactures other worlds as a routine byproduct. The search also descends to the smallest scales. Massive particle colliders, far more powerful than any we have today, will push into uncharted energetic territories. They will hunt for particles predicted by theories like supersymmetry, a key ingredient in many versions of string theory. Discovering this shadowy sector of particles would provide powerful, indirect support for string theory and its staggering landscape of 10 to the 500 possible universes. It would lend credence to the idea that our physical laws are just one possible setting on a vast cosmic control panel. Conversely, if all these searches return empty-handed, if no supersymmetric partners are found and the colliders see only the familiar particles of the standard model, the case for a string theory landscape and the Level Two Multiverse it implies would be significantly weakened. The ultimate goal, the holy grail of fundamental physics, remains a complete theory of quantum gravity, a single framework that seamlessly unites the cosmic realm of general relativity with the subatomic world of quantum mechanics. Such a theory would not be built on guesswork. It would show us with mathematical certainty whether the existence of other universes is a forced, inescapable consequence of the laws of physics, or merely an attractive but ultimately avoidable possibility. The future of the multiverse hypothesis, therefore, does not rest on a single, spectacular discovery. Its fate will be slowly sealed through a multi-pronged assault, a convergence of cosmology, particle physics, and pure theory. Each new piece of data, each refined measurement, and each theoretical breakthrough will slowly turn the key, either unlocking a cosmos of infinite realms or forever sealing us inside our own solitary, and suddenly much lonelier, universe. Accepting the multiverse would shatter our cosmic address in a way not seen since Copernicus. He showed us our world was not the center of the universe. Darwin revealed we were not the pinnacle of creation. Now, the multiverse threatens the ultimate demotion, suggesting our entire reality is not the main event, but a single scene in an endless cosmic drama. We would no longer be the center of existence, merely residents of one neighborhood in an infinite metropolis. This is a humbling thought, a profound stripping away of our special status. Yet, in that very humility lies a breathtaking expansion of grandeur. The cosmos becomes a place of unimaginable richness, a tapestry woven with threads of every conceivable pattern. Our universe, with its specific laws and particular history, is not the whole story, but one volume in a library containing every story that can ever be told. The quest for proof continues to drive experiments at the frontiers of physics, from peering into the cosmic microwave background to smashing particles in colossal colliders. Even if the final, direct evidence remains elusive, the journey itself has already transformed our understanding. It has forced cosmologists to ask deeper questions about the origin of our laws, pushed quantum theorists to confront the nature of reality itself, and invited philosophers to reconsider the meaning of existence. This intellectual ferment is a testament to the power of a radical idea. It reminds us that the universe feels no obligation to be small, simple, or intuitive. Our human-scale expectations, forged on a single planet orbiting a common star, are a poor guide for the true, sprawling architecture of everything. The multiverse may forever remain a hypothesis, but by its very proposal, it has already succeeded in expanding the horizons of the possible. Our journey through the multiverse ends not with an answer, but with a question that echoes across the cosmos. We have navigated the solid ground of eternal inflation, wandered the branching paths of quantum mechanics, and glimpsed the vast landscapes of string theory, each pointing toward a reality far grander than our own. These are not just fantasies, but serious extensions of our most successful scientific frameworks, offering elegant solutions to profound puzzles like the universe's suspiciously perfect fine-tuning for life. Yet, we must also stand in the shadow of legitimate critique, acknowledging the formidable challenge of testing a hypothesis about realms that may be forever beyond our reach. This is the essential tension, a frontier where rigorous science meets the deepest philosophical speculation. The multiverse remains an unproven, breathtaking possibility. Its true power, however, may lie not in its ultimate verification, but in the journey of thought it demands from us. It forces a radical expansion of what we consider possible, challenging our most basic assumptions about reality, uniqueness, and our place in the grand scheme. Whether this idea is someday confirmed or gently set aside, the act of pursuing it embodies the very spirit of science, the relentless drive to look beyond the horizon and ask what else is out there. It invites us to marvel at a cosmos that feels no obligation to be small, simple, or centered on us. Let this exploration be a reminder that the universe's greatest mysteries are invitations to dream bigger, to question more deeply, and to forever remain students of the infinite. We would love to hear your thoughts on this mind-bending topic in the comments below. And if you want to continue exploring the edges of understanding, be sure to subscribe for more journeys into the unknown.